Perhaps I prepare a bit more slides than it's necessary for 30 minutes talk, and then maybe I will skip some of them, at least with some ideas of proofs. But my idea is to explain the current situation in this, at least from my point of view, very interesting topic about approximation. Today I will restrict myself to the uniform case, uniform approximation of functions by solutions of elliptic equations and systems. Well, and just immediately I need to say that when I use the term equation, I also think about systems, because in this subject we're working with elliptic equations with constant but complex coefficients, so it's some kind of system with additional symmetry. Well, and I try to explain more or less the following three directions, the following three plots in this very wide area. And the first picture, the first plot, is related with properties of capacities determined by elliptic operators with constant complex coefficients. And in this plot, I will work in the space Rn with n greater or equal than 3. In this subject, there are several recent results and advances in studies of the capacity, which I define in a few minutes. Well, the second plot is the case of uniform approximation by polynomial. It's important solutions of also elliptic operators with equations with constant complex coefficients on compact sets in the plane. And here I want to discuss two distinct cases. The case of strong elliptic operators, where there is a very interesting conjecture about analog of Walsh-Lebesgue theorem, and the no strong elliptic case, where the results about possibility of approximation is controlled by very interesting and a bit unexpected analytic characteristics of compact sets where we consider our problem. Well, and the last plot, if time permits, will be related with the Dirichlet problem for these equations, because it's one of the main ingredient and one of the main difficulty related with the previous plot, related with the Walsh-Lebesgue type result for these equations. So this is the plan of our discussion. Well, and let me switch to the first plot. So first of all, I'm going to define capacities related with second order elliptic equations with constant complex coefficients and okay, in capacities of sets in Rn. So the definition is in the screen. Perhaps I will not read it, but okay, I will try to use this one. Well, so how we define this capacity? We have L, our elliptic operator, second order, with constant complex coefficients. Phi L is a fundamental solution, and for some bounded set E in Rn, we define this capacity gamma L. Okay, here these brackets mean the standard action of a distribution on a smooth test function, and we take a supremum over all complex valued distributions with compact support on E, such that the convolution of our fundamental solution with this support is just an infinity function, and whose infinity norm is less than 1. So if we restrict here ourselves by the class of distributions which defined by positive Borel measures, we obtain so-called positive, or also it called metrical version of our capacity, the capacity gamma L plus. So the notations are got from the classical analytic capacity gamma and positive analytic capacity gamma plus, which is the subject of a very intensive study from last maybe 40 or 50 years, because the meaning is more or less the same. Also, we need two more capacities, the capacities alpha and alpha plus, which can be defined by the same way, with the such difference that we use distributions such that this convolution is continuous in all space, and of the same alpha plus. This in the definition of this capacity, similar to gamma plus, the supremum is also taken by positive Borel measures with the same property, of course. Well, it's from the first point of view, it looks some very specific characteristics of set, but what's possible to say just immediately? If we have our operator to be a Laplace one, then all these capacities are the same. All these capacities are the same, and it is a typical classical harmonic capacity or Wiener capacity, which is very well known, and this capacity can be described in pure metrical terms. Okay, it's just a corresponding transfinite diameter in the respective dimension. Of course, this characteristic is countable as semi-additive and have many interesting properties. What's about these capacities gamma L, alpha L, etc.? Of course, we have the same questions. The first one is the question about comparability of these capacities, and of course the question on comparability of this capacity with the harmonic one. The question, of course, about semi-additivity of these capacities and their metrical description. And in some sense, the separate case is the case how to describe zero sets of these capacities. Why it's of interest? It's just because the zero sets of capacities gamma L and alpha L are exactly the sets of removable singularities for solutions of our equation LF equals 0. Okay. In the case of approximation, just to describe the interest to these capacities from approximation point of view, I present a recent result by our colleague Maxim Mazalov from Smolensk, who recently proved the following theorem. I mentioned here just the journal and here, but it's quite easy using this data to find the paper. The result is the following. We have an arbitrary compact set in Rn. We have a function f continuous at this compact set, and such that this function satisfies our equation Lf equals 0 on the interior of X. And we ask whether or not it's possible to approximate this function by functions satisfying this equation in the neighborhood of X. So it's similar to classical problem of approximation by rational function, for function of a complex variable in the compact set in the plane, by, for example, rational functions with poles located outside the set where approximation is considered. And the answer is the following. The approximation is possible if and only if we have the following estimate for so-called L oscillation of our function over an arbitrary ball in Rn. So what is this L oscillation? Here there is a general formula. L here is just a symbol of our operator, and all other elements of this formula seems seems easy. Okay, to understand this formula better, I emphasize that in the harmonic case, this harmonic oscillation is just a difference between the average of our function over the sphere and over the corresponding ball. So, yes.
Does the sign meaning? I mean.
You mean this sign?
Yes.
Yes, it's exactly, because just by the mean value theorem, if our function is harmonic, then this is the value in the center, and this is the value in the center. And what this quantity, what this oscillation, in some sense measure? This measure a total mass of singularities of our function that are located in this ball B. And what we need, and we need that this mass of singularities should be controlled by this capacity, which in some sense also the mass of singularities, but of the whole class of functions that we will want to use as an approximants. And no, of course, this is the technical items like a modulus of continuity, okay, some delta related with the dimension. But the important is that if we are able to control the mass of singularities of our function by the total mass of singularities of the function which we use as an approximant, then the approximation is possible. Well, and no, of course, it's just this theorem also has a very long history, and unfortunately, I have no time to enter deep to this topic. Well, but what I want to formulate more about this result is that using the previous result, it's possible to prove the approximation criteria for classes of functions. You see that here we're working with an individual function. And now we ask the standard question also in this direction. What is the conditions on a compact set X under which any function which is continuous on this compact and satisfy the equation in its interior? So it's a trivial necessary conditions for approximation, and we are interested when this natural necessary condition is also sufficient. And the answer is the following: we should have this equality of capacities, which also points us into the same direction. Here we have a total mass of singularities of functions under approximation, and here is the total mass of functions which we use as an approximant. Of course, this result is very interesting to compare with the classical Vitushkin theorem about uniform rational approximation. In the case of individual function, the important ingredient here was the just estimate of integral of a function of the complex variable over the circle, an arbitrary circle, and with the, of course, Keldysh-Denny criteria for uniform harmonic approximation. It's interesting that the first result about this type of approximation was formulated not in the terms of harmonic capacity, but in terms of regular and irregular points, the classical Keldysh-Denny theorem. And only later on it was reformulated in terms of harmonic capacity, but only for classes of functions. And what is very curious and interesting that this result for harmonic functions, it's also rather new. It was proved approximately in 2010 or 11, something like this. So the criteria for individual harmonic approximation included into this theorem is also very recent result. Well, so this theorem is of course the motivation to study properties of these capacities, no, just as the Kvitushkin criteria starts the 50 years investigation of properties of analytic capacities, and what we was able to prove with my colleague Peter Paramonov from Moscow University, we was able to prove now for positive capacity, for capacity gamma plus, we prove that in any case, in the okay, that this positive capacities in the case of dimensions 3 and 4 are comparable with the classical harmonic capacity. Moreover, we prove this comparability also in a case of dimensions bigger than 5, but under some additional technical condition, which was avoided also very recently by Maxim Mazalov. So now this is the result valid for all dimensions, that the capacity gamma L plus is comparable with the harmonic capacity in the corresponding dimension, so that this capacity is also described in terms of, for example, transfinite diameter in the corresponding dimension, and of course semi-additive, which is very important for approximation results, as I mentioned. And moreover, there are several preliminary results pointing us that in fact the comparability of gamma L and alpha L with harmonic capacity also should be true. And of course I have no time to enter into the proofs, but I want to highlight here that the essential problem is that this kernel or phi L or fundamental solution in this situation is not odd, and it cause a lot of new, in principle, new difficulties, which was not appear in the case, for example, of analytic capacity in the case of analytic capacity in the plane. But here the results sound very, very interesting. Well, so this is the first topic, and this is the first result that I want to explain. And okay, let me skip the sketch of the proof just because I have approximately 10 minutes, no more. Well, the second topic, the second plot, is related with the following Walsh-Lebesgue theorem about harmonic polynomial approximation. In fact, this theorem is the first, in the historical point of view, the first result of such type, no, just after the classical Runge theorem, because the first one was Runge theorem. But in the case of Runge, we have functions, okay, in the Runge situation, holomorphic in the neighborhood of a compact where we consider the approximation. But later on, the question was posed about approximation of function which is just continuous on a compact set and analytic or holomorphic or satisfying some other elliptic equation only in the interior. And the first result in this direction was the following Walsh-Lebesgue theorem. It's approximately 1929, year 1929, and the theorem is the following. Okay, we have a compact set in the plane, and we're interested when any function which is continuous on this compact and harmonic on its interior can be approximated uniformly on X by harmonic polynomials. Harmonic polynomials, it's just the polynomials in two real variables with, for example, complex coefficients, if we're thinking here about complex valued functions, just satisfying the Laplace equation, so that it's a sum of holomorphic and anti-holomorphic complex polynomials. Well, and the criterion is the following one. It's this approximation is possible if and only if X is a so-called Caratadori compact set, which means that its boundary coincides with the boundary of its topological hull or polynomial convex hull. Some people know this notion with different names, but it's nothing more than the union of our compact set X and all bounded connected components of its complement. The term caratodary compact set, of course, comes into mathematics approximately 50 years later than the theorem was proved, but okay, the important is this property of X. Well, actually this result was proved by Walsh, but why nowadays it's known as the Walsh-Lebesgue theorem? It's just because the Lebesgue theorem about solvability of the classical harmonic Dirichlet problem in an arbitrary bounded simply connected domain in the plane is an important ingredient. Of the proof. Well, this is the result, in some sense model for us, and we approximately 20 years ago we asked the question, what's happened if we replace here the harmonic functions by solutions of some elliptic PDE with constant complex coefficients, and of course we want to approximate this function by also polynomials from the kernel of the corresponding operator. Okay, and up to now there is a conjecture that the same approximability criteria holds in the case of approximation by polynomial solutions of general second order, but it's important, strongly elliptic even systems with constant coefficients. The sufficiency so if our compact set is a caratodary 1, then the approximation property mentioned above is possible. It was proved in approximately 20 years ago by our student Alexander Zaitsev from Moscow, but his proof works only for equations with complex coefficients. For general systems, it's up to now an open problem. And of course, the most important situation is the most important problem is to prove the necessity of this condition. It's not possible to follow the scheme of Walsh-Lebesgue theorem just because we have not results about general solvability of Dirichlet problem for such equations in general simply connected domains, no, at least in caratodary domains, because all known results, of course, are used very strong restrictions on the smoothness of the boundary. Well, no, okay, here perhaps I need to skip this because here I briefly explain how to write solutions of equations and systems under consideration in the complex form. Let me concentrate only in the case of operators with constant complex coefficients. So in the strongly elliptic case, any solution can be represented in the following way using a pair of galomorphic functions of the arguments. Here the tau is this perturbation of complex variable, but since the parameter tau is a canonical parameter which depends on this A, B, and C, and since this parameter is between 0 and 1, this variable is in some sense more close to the complex variable z than to z bar. And for example, with tau equals 0, here we have a representation of harmonic function as a sum of holomorphic and anti-holomorphic counterparts. And here is something more involved in the case which is not strongly elliptic. Well, and okay, here this is the situation related with general systems. Unfortunately, I have no time to explain. And well, so and let me give some preparatory results about our approximation property. This is the analytic characteristic of a domain, which I announced in the very beginning of my talk. I assume that we have an operator. We have a strongly elliptic operator in both cases, tau from 0 to 1. And in this case, we call a domain so-called L special if we are able to find two functions, f and f tau, galomorphic. This function is galomorphic in C is a complex conjugation. C here is a complex conjugation operator, and T is a linear operator which maps Z to this Z bar. So so there's two functions galomorphic in different domains related by this operator, such that for any accessible boundary point, the boundary values of these functions at this corresponding points coincide. The same situation is for not strongly elliptic case, but here this function is galomorphic in the initial domain itself, and of course here there are no complex conjugation as here. Also, the same notion can be introduced for two different values of tau, which will be need a bit later. And what is the result? The result is the following one. Assume there is a Caratadori domain in the complex plane. So this Caratadori domain is the domain whose boundary also coincide with the boundary of unbounded connected component. Okay. Of its complement. And the result is the following one. Any function continuous in the boundary of the domain can be approximated uniformly by, okay, here analytic functions, so the solutions of our equation with singularities outside of the closure of the domain. Just after that, using the Runge method, etc., it's possible to derive from this the polynomial approximations result, if and only if this domain is not L special in the sense of this definition. Well, in particular, if the closure of this domain does not separate the plane, then we have exactly the result of a polynomial approximation. And moreover, every Caratadori domain is not L special in this situation. It's possible to understand appropriately using the argument principle, just because this variable t zeta or z tau is more close in the sense of changing of argument to z. And here we have that there are two galomorphic functions which turns the argument in the opposite direction. So this is just an idea, but of course there are several technical steps to prove. Well, and perhaps I need to more or less to stop here. I just only to show what's happened in the case of general systems, not only the systems related with operators with complex coefficients. In general system, the situation is much more difficult and in some sense hidden, just because our main tool, the dual approximation method, based on using of so-called orthogonal measures, leads to very strange properties of measures, very strange properties. And what was possible to prove, just have 20 seconds, is just this result, where in the case of general operators we are able to say something, but when we approximate continuous functions by sums of polynomials from kernels of two distinct operators of our type. Well, so this is the moment to stop. Unfortunately, the third plot, it was not enough time even to touch. So thank you for your attention. If there are some questions, I will try to open.